Hello again, it is Mr. Boothman yet again. We are talking about section 3.2 this time, logarithmic functions. So I think most of you are familiar with logs. If you're not, that's okay. This is a great introduction. And even if you are, I think that you'll deepen your understanding of logs as we go through this section. So we're going to start with what logarithms are. So every exponential function is a one-to-one function. No matter what our exponential function is, it passes the horizontal line test. So it is one-to-one. That means it has an inverse. How do we write this inverse is the question. Some of you might be saying, well, what about the square root? We will talk about why we need both square roots and logs in class. There's a mathematical reason for it. But basically, how do we find an inverse of a function? Well, we switch x and y, and we solve for y. So if I start with an exponential function, y equals b to the x, I switch x and y, and I solve for y. I'm stuck. Any ideas? How do I solve for y there? I can't just take the square root. That won't get me y. I can't do any operation that I can think of. So basically, we created an operation. We created the inverse of an exponential, and we called this the logarithm with base b denoted log base b x. So, bit more of a definition of a logarithmic function. Let b be a positive number, and b cannot equal 1. And we'll see why b can't equal 1 once we actually get more familiar with the log function. But the logarithmic function with base b, denoted by log base b, is defined by log base b of x equals y. And we see that we get this from b to the y equals x. So if you want to, basically, if you want to think about it this way, log base b of x is the exponent to which the base b must be raised to give x. I define y as this. Y was my exponent. So you see, log base b of x is the exponent I have to raise my base to give me x. Now, if you're like me, when I was first learning logs and converting between logs and exponentials and thinking about this stuff, I was very confused. I had to really think about it. At first, I just memorized it. Unfortunately, when in my math classes in high school, I could just memorize things and do pretty well. But in college, I developed a much deeper understanding of logs and exponentials and the relationship between them. So I want you to develop that deeper understanding now, rather than later. So if you need to reread this definition or rewatch the video, if you need to write down questions, I really do want you to understand what the log is in relation to the exponential function. It is the inverse. It will undo the exponential function. So a couple more pieces of terminology. Y, in either of these formulas here, or here, y we call our exponent. B we call our base, just like exponentials. And x is what we call the argument of the log. The argument. So, if you hear me refer to the argument of the logarithm, I'm talking about the x there, or whatever happens to be in x's position. So one more time, because it is so important. Log base b of x equals y is my logarithmic form. My exponential form is b to the y equals x. Memorize this. I just said I want you to develop a deeper understanding, and this is true, but I also want you to remember this. I don't want you to confuse the b's and the x's and the y's, because if you do, this unit's going to be kind of difficult for you. So think about this, understand where it comes from, and make sure that you understand, you know these two formulas by heart. I can't stress how imperative that is. enough. So, one last thing about logs. If this is my function here, can x ever be negative? Can x ever be negative? Well, look at the exponential. They're the same numbers, just written in a different form. Can x here ever be negative? Can I ever have a base raised to a power that gives me a negative number? No. Can x ever be 0? Again, look at the exponential form. Can I ever raise a base to a power and get 0 as an answer? No. So these are two further domain restrictions for logarithms. I warned you way back when we talked about domain in section 1 or in unit 1 that there were a few more restrictions that I wasn't talking about at the time. It's because we hadn't talked about logs yet. So here they are. The argument of the log can never be negative and it can never equal 0. Y can certainly be negative or equal 0. The base, well, we're not actually plugging in numbers for the base, but the base could be 0 as well. So let's take a look at some examples. If you're still with me, I hope you are. Let's convert between log and exponential form. Just looking at these two forms up here. So log base 10 of 100,000 equals 5. In exponential form, that looks like 10 to the 5th equals 100,000. That should make sense to us. If I was just evaluating 10 to the 5, it would be 100,000. So I'm just moving between the two forms. Now I'm moving backwards this time. 2 cubed equals 8. Well, I have the log. My base is the same as the base of my exponential form. So log base 2 of 8 equals 3. So this is how I move back and forth, how I convert from exponential to log form. Here I have 2 to the negative third power equals 1 over 8. Again, that should make sense to us. By my negative exponent rules, I can move the 2 cubed down to the denominator. I'll have 1 over 8. And then finally, moving backwards again, I have log. My base is the same, base 5, of s equals r. So, very briefly, that's how I move back and forth, how I convert between log and exponential form. It's very important that you're comfortable with that throughout this unit. One more brief bit of information to give you before we really dive into this. Anytime that you don't write the base of a log, or anytime that you see that the base of a log is not written, it just looks like this, log of x, it is assumed that the base is 10. Log base 10 of x. The 10 is assumed, so base 10. Common. It's called the common logarithm. All right, moving on. Let's talk about evaluating logs. There are a few steps to this. Basically, the easiest way to evaluate logs is to convert them to exponential form and then find equal bases if you can. So let's see what I mean by that. Here I have log of 10. I just said if the base is not written, it is assumed to be 10. So I'm going to convert this to exponential form. I'm going to set this equal to x since I'm looking for the answer. Whenever I'm looking for something, I use x as my variable. So this in exponential form would be written as 10 to the x equals 10. Well, what's my power here? My power is 1. So x must be 1. Make sense? Let's try another one. Here again, my invisible base is 10. I'll set this equal to x. So I have 10 to the x equals 1,000. All right, let's think about this. What is if I have equal bases, so what I mean is I have 10 over here, I want to write 10 over here. So I'm going to need to rewrite this as 10 to some power. 10 to the third power gives me 1,000, and that means that x must equal 3 if these are equal. So that's what I mean by having equal bases. Let's look at another one. So this time my log has a base of 2. I have 2 to the x equals 32. Again, I want the same base, though. So I'm going to rewrite 32 with a base of 2. And what exponent will I need to give 2 to equal 32? I happen to know that this is 2 to the 5th. Promise you'll get more comfortable with this. That means x has to equal 5. Here, my base is 10. So 10 to the x equals 0.1. 0.1, of course, is 10 to the negative 1 power. Oh, I'm sorry, negative 2 power. No, wait, it is negative 1. Disregard your teacher momentarily. So I have x equals negative 1. And then finally, 16 to the x equals 4. Well, this one's a little trickier. I want the same base. So how can I write 4 with a base of 16? Well, I know that 4 squared is 16, so 16 to the 1/2 is going to be 4. Hopefully you're comfortable with fractional exponents. Fractions are the same as radicals when we're looking at exponents. So that means x is going to equal 1/2. So my steps to evaluate. First, I set the log equal to x. Then I convert to exponential form. Then find equal bases, and then solve for x. Solve for x. Okay, my 4 steps. All right, moving on, because I feel like this video is going to be a little long. I'm sorry. This is a long section, but we'll spend a lot of time on this in class, so that's why this has to be so long. So next we're going to talk about graphs of logarithms. So we talked plenty about exponential graphs last section. This time we're talking about logarithms, but we said that the logarithm is the inverse of the exponential. When I have the inverse, all I have to do is switch x and y. So if I get my list of points here from my exponential function, I should still have that from my guided notes from section 3.1. To get my logarithm points, all I have to do is flip them. Literally, switch x and y. And now, let's take a look at how these two graphs look. So here's 0, 0. I'm sorry, I know it's a little hard to tell. Here I have negative 3, 1/8, negative 2, 1/4, negative 1, 1/2, 0, 1, 1, 2, 2, 4, and then 3 way up here is 8. So that's my exponential function. Let's graph my log function now. I have 1/8 negative 3, 1/4 negative 2, 1/2 negative 1, 1, 0, 2, 1, 4, 2, and then 8, 3 is going to be way over there. So interesting. So if you remember, I very, very briefly said when we talked about inverses that inverse functions are reflected over the line y equals x. And that's because we're switching x and y. It's reflected over that line. So if I very quickly sketch that line, y equals x, you can see that my functions are indeed reflected over that line. Very cool. I love math, so I teach it. Okay, so graphing logarithmic functions. We can talk about transformations again. They're the same as before. Exact same as before yet again. So A will give me a vertical stretch or compression. C will be a horizontal stretch or compression. H will be a horizontal shift. K will be a vertical shift. Then my reflection, if I have negative A, will be a reflection over the x-axis. If I have negative C, it's a reflection over the y-axis. So all the same as before. So shouldn't be anything new or scary for you. But for now, I want to talk about this. Graphing logs. It's a little different compared to graphing exponentials. And that's because the whole notion of log is tied up with the exponential. In fact, for graphing them by hand, and I promise I won't make you do this too much, since we do have calculators, but for graphing log functions by hand, you really need to know the exponential function. And then it's the inverse, so we flip it. We switch x and y. So here, looking at this f of x, what is the exponential parent function? The exponential parent function, well, we come back up here. I had y equals 2 to the x. That was the inverse of y equals log base 2 to the base 2 of x. Here I have a log base 3 of x, so my parent function, my exponential parent function, is going to be f of x equals 3 to the x. So down here I can write 3 to the x. That means my anchor points for the exponential are 0 and 1, and 1 and 3. My logs then, I switch x and y. So for my log function, I'm switching x and y. So instead of 0, 1, I have 1, 0. Instead of 1, 3, I have 3, 1. And now, just like before, I am mapping the transformations in order of operations. So there's a shift to the right by 3. That means if I'm shifting to the right, I'm adding 3 to x. So I have 4, 0, and 6, 1. This 2 out in front is a vertical stretch by a factor of 2. I multiply my y's by 2, so I still have 4, 0. And then I have 6, 2. And then minus 4 is down by 4. So I'm subtracting 4 from each of my y coordinates. So I have 4, negative 4, and 6, negative 2. All right. Now I need my vertical asymptote. So you'll notice that here, I did have a vertical asymptote for my log function. Should have used a different color. I do apologize. That was the line x equals 0. My log function approaches that vertical asymptote. So here, I am shifting x to the right by 3. That means I'm going to have a new vertical asymptote at x equals 3. So log functions have vertical asymptotes. Exponential functions have horizontal asymptotes. Remember that. And then they're shifted according to the shifts in my y or my x. And now I sketch my vertical asymptote and plot my anchor points, and then I can draw my curve. So x equals 3. Here's my asymptote. My anchor points are 4, negative 4, and 6, negative 2. And then sketch my smooth curve. There's my log function. All right, I promise we don't have too much left in this section. The last couple pieces are pretty short and sweet. But I do want you to make sure that you understand this process of graphing. Like I said, I won't make you do it by hand very much, but it's still important to be able to do. So let's take a look at the natural log function now. Once you've looked over and you feel comfortable with graphing log functions. The natural log function. Remember I talked about exponential natural functions, the natural exponential function with the base of e. Natural log function is the same. In fact, it is the inverse of the natural exponential function. We still have a base of e. So whereas here I had f of x equals e to the x, now I have log base e of y equals x. Make sense? So I graph it just like normal. Sorry, I'm not sure why I just paused there. The natural exponential function, I had these points from before, 0.05, 0.14, 0.37, 1, 2.72, 7.39, and 20.01. For my natural logarithmic function, all I have to do is flip them. So 0.05 and -3, 0.14 and -2, 0.37 and -1, 10, 2.721, 7.392, and 20.01 and 3. And then I can graph these. -3, 0.05, -2.14, -1.37, 0, 1, 1, 2.72, 2, 7.39, that's somewhere way up here, and then 3 and 20 is way up there. Now I graph my log function, 0.05, -3, 0.14, -2, 0.37, -1, 1, 0, 2.721, 7.39, 3, that's way over here somewhere. I just missed all of those points. Fantastic. And then we can plot y equals x again to see that symmetry, to see that reflection. So pretty. I love it. And there's the natural function, the natural log function. So one last very important piece about the natural log function is that we usually don't write log base e. This shows up so often that we have special notation for it. We write ln for the natural log. And then this could be ln of 4 or ln of y. Regardless, the base e is understood. We don't actually have to write that. All right. Natural log. Oh, I'm not just sure what happened. That's great. Sorry about that. Properties of logs is the last part of this section. Again, this video is getting so long, I'm sorry. I'll try to rush through this last part as quickly as I can, but as clearly as I can. So there are a few properties of all logs that will be very helpful to us when we're working with logs throughout the rest of the unit. I realize I just said logs about 5 times in that sentence. Apologize. First, the log of 1 equals 0. So no matter what our base is, our base could be anything. Our base could be e, it could be 10, our base could be 3. No matter what that base is, the log of 1 equals 0. Why? Because whatever that base is, it must be raised to the 0 power if we want it to equal 1. Remember, I'm going from my base here equals this. So here, 10 to the 0 power equals 1. -2 to the 0 power equals 1. E to the 0 power equals 1. All right. Next, we have log base b of b equals 1. Again, so no matter the base, whatever b is, I want b raised to some power equals b. That has to be 1. It has to equal 1. So that's where that 1 comes from. For a very similar reason, if I have log base b of b to the c, that answer is c. I have b to the, when these videos get long, word starts acting strangely here. So if I have b to this, whatever this power is, equals b to the c. So this power has to be c. Has to be. C equals c. Couldn't be anything else. And our very last property of logarithms that I'm going to talk about today, if I have b raised to the log base b of a, if I have b raised to this really weird exponent power, that equals a. It equals a. Remember that log base b of a means, well, if we evaluate that, what is that going to equal? It's going to be b to what power equals a. So that'll just give me a number. It will give me the exponent I need to raise b to get a. And then if I'm raising b itself to whatever that exponent is, I'm going to get a. Just going to. So again, that's very subtle. Go ahead and think about it, pause it, come talk to me if you need more clarification. But last section, we can very easily evaluate these logs using our properties. So log base 5 of 1 is 0. Has to be, by this first property. Log base 5 of 5 is 1. Again, by this property. Log base 5 of 5 to the 8th, we're looking at this property, it's going to be 8. 5 to the 8 equals 5 to the 8. Shocking, I know. 5 to the log base 5 of 12 is 12. That's looking at our fourth property here. Log base 5 of 12 is going to give me the power I need to raise 5 to get 12. So if I'm raising 5 to the power I need to raise 5 to get 12, I'm going to get 12. Here my e is understood as the base with the natural log notation here. So I have the same base and argument. That means I'm just going to have 8. This last question is a little trickier. I'm going to rewrite this as the natural log of e to the negative 2. This will make it easier for me to see that the answer is negative 2. All right, that was a very long section. I apologize. This video is now at 27 minutes and 45 seconds, but we're done. There was a lot in here. It's going to take us a while in class to unpack all of this, but please rewatch parts of this that confused you and make sure that you feel confident with this. And we're going to spend plenty of time practicing this in class and get your questions answered. So thank you so much, and have a great day.